So we would like to compute the second order partial derivative fxy. And it's important to remember that for nice functions like the one that is given to us, well, nice not in terms of how complicated it is, but in terms of the fact that it's differentiable as many times as we'd like. But for such functions, the order in which we take the derivatives doesn't matter. I'm not sure this is something that we're going to use in this particular example, but it's something worth remembering. The idea here is that we should first take the derivative with respect to x, in which case we're going to use the product rule and the chain rule, and then whatever comes out of that process, we will have to take the derivative for that with respect to y. So it's going to be pretty complicated. Let's pay attention. Let's make sure that we get all the steps correctly. In particular, think of it at first as a product of two functions, like so. And this means that the derivative with respect to x will be the derivative of the first function with respect to x. So now y counts as a constant, and the derivative is y squared. And then we multiply this by the second function. And then we take the product of the first function unchanged times the derivative of the second function. And what is the derivative of the second function? We have sine of a quantity, and the chain rule dictates that the derivative will be cosine of the same quantity plus the derivative of that quantity. And the derivative of that quantity with respect to x would simply be 3x squared times y. Let's explain how that works. So the quantity we're talking about is this x cubed plus y to the fourth. And since we're differentiating with respect to x, y counts as a constant, and the derivative of y to the fourth is simply 0. So all we need to do is take the derivative of x cubed times y, which is 3x squared times the constant y. And that's the derivative with respect to x. So now we want to pile on this and take the derivative with respect to y. Okay, so this is where we might want to take a deep breath and actually consolidate a little the second component, because otherwise we will have three functions of y. So let me postpone this for a second and just rewrite this as y squared sine of x cubed y plus y to the fourth. And the second one, as I said, let's bring all the powers together. So we have a 3, then we have an x cubed, then we have a y cubed, and then we have a cosine of x cubed y plus y to the fourth. In most cases, we won't need to do something like that, but I think here it's quite beneficial to do it, because now each of these summands can be considered as a product of functions in y. So now I think we're ready to do this. And again, let's just recall that the first function is a product of two functions of y. And the second summand is also a product of two functions of y. So we really have two problems in our hands that look very much like the initial differentiation that we made. So let's finish this. So this will be 2y times the second function, and then plus y squared times the derivative of the second function, which is sine of a quantity. So again, the chain rule implies that we will have cosine of the same quantity times the derivative with respect to y of that quantity. And now the derivative with respect to y is a little more interesting, because we have two terms containing y. So it will be x cubed, that's the derivative of x cubed y, plus 4y cubed. Okay? And then we will have plus. Let's put the plus indicating that we're continuing on the next line. And we want to take the derivative of 3x cubed y cubed. So that will be 3x cubed, treat this as a constant, times 3y squared, times cosine of x cubed y plus y to the fourth. And then again, by continuing our product rule, we will have 3x cubed y cubed times, and now we want the derivative of cosine of a certain quantity. The derivative of cosine is negative sign, so we will have negative sign of the same quantity times the derivative with respect to y of that quantity, and this will be x cubed plus 4y cubed, something that we have already encountered. And yes, the final answer is very, very complicated. It's quite unlikely that one would ever use this in a specific problem for anything other than differentiation practice. But it's a good idea to do an example like this every now and then to make sure that we can get all these rules straight and we can sort things out correctly. And that's all. Thanks for watching.